Hey folks, today's topic is derivatives on the calculator, and believe it or not, this is a one-page notes, OMG, and we have a one-page homework assignment. Man, this never happens in AP. All right, so how to do the derivatives on our calculator. Now, the AP test has a non-calculator free response, has a non-calculator multiple choice, but then it also has a calculator free response and a calculator multiple choice. So you do want to save, if you can do some of these derivatives on your calc, you're going to want to save that time and not have to do it by hand. And sometimes you get something that, well, we're going to learn how to do all these derivatives actually by hand, but right now we don't know how to do those derivatives by hand. So we have this shortcut. So there's two ways. Let me see which calc this is. Okay. There's two different operating systems that you're going to see on the TI-84. I have the math print, which looks fancy. The derivative at C is this thing. We want to select math 8 from the home screen. So I could either go math and then down to number 8, N derivative. I can hit that. Or if you want, you can hit math and just hit the number 8 and it'll bring you there as well. Now you have the old operating system. When I hit math 8, it brings me to this thing. So I'm going to show you how to type both of these in when we do some examples. If you have the fancy operating system, I actually don't use math as much anymore because I've got everything good is underneath these two windows. So if I hit alpha F1, remember that's where I can make a fraction. But if I hit alpha F2, I have n derivative right there, and then I don't have to hit math 8. Maybe it's quicker to hit just math 8. Doesn't really matter to me which way you do it. I just want to show you that both ways are possible. Okay, so let's now actually calculate a derivative on our calc. So evaluate the following: f prime of 4 if f of x equals natural log of x. So that means I want to figure out the slope of the tangent line when x equals 4 for this function. But since we get to use our calculator, we don't have to overthink this. So I'm going to hit alpha F1. I'm going to go to select my... Now, dd, that's the derivative that I'm deriving according to. So this should be ddx. So I'm going to select the x button that we usually put in when we're graphing. Then in here goes my function. So for us, that's natural log of x. Now be careful. When you hit natural log, it brings up a parenthesis for you. So you got to make sure that you close that parenthesis. There's a parenthesis for a set of parentheses for the derivative, and then you're going to need another set for the natural log. And then here I derive according to whatever I want. This is the x value at which I want to derive. So here I would put in 4. You should know, we talked about this last year in pre-calc when we did maxes and mins. You should know this number is 0.25. This number is 1/4. Anytime you see this sort of craziness. Now, in chemistry, that's not true. Because in chemistry, they have these really, really weird numbers. The atomic weight of, I don't know, a hydrogen atom is something like this. So these numbers do matter in chemistry. In math, you've got to understand that this probably should be 1/4 or 0.25. So I can now write down here that f prime of 4 is equal to, and I'm going to write it as 0.25. You could write it as 1/4 as a fraction as you want. Now let's see if that makes sense graphically. Let's see if this is a reasonable estimation of the slope at 4. So I'm going to give you 10 seconds. No, I'm going to give you 5 seconds. Sketch the natural log graph. 5, 3, 2, 1, 0. Natural log graph looks like that. So if I were to draw the tangent line over here at x equals 4, I don't know exactly where 4 would be, but it'd be somewhere over here. Something like that. Does that seem reasonable that that slope could be 1/4? I mean, yeah, I would guess that it probably is. I mean, I mostly am just looking that it's positive, that slope of the tangent line would be positive over there. So yeah, that seems like a reasonable answer. Okay, let's say you don't have fancy calc. Let's say you have the old classic print. So I'm going to go math. This time I have to do math 8. Now here I want to put my function. So my function is the natural log of x. Close it. Then I want to put a comma. What am I deriving according to? X at what value 4? And it should spit back the exact same thing. So this is the function. then the variable of differentiation, and then the constant. Yeah, let's have you try this one. Let's see how you do there. Pause it, give it a whirl. All right, let's see how you did. So, alpha F3, F2, I mean. I'm deriving according to x. I'm going to now put a fraction back in there because I have the new fancy print. X squared plus 1, 2x plus 5. I'm going to derive this at -2. Oh, why did I hit graph? Hit enter. I get -38, blah, 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 which we know really is -38. So y prime of -2 is equal to -38. Now, there's another way to do this. So there's that method, and then sometimes we're going to be looking at the graph, and it's easier to actually do the derivative right from the graph. So let's say that here's another method. Here's the graphical method. So I'm going to go in here. I'm going to input this as my function. So 3x squared plus 1 over 2x plus 5. I'm going to do a zoom 6 to give me a decent window. Good enough. I don't know. That's good enough. Because where are we looking? We want to look where x is -2. Our graph covers that, so we're fine. So I'm going to go now. Everything when your graph, everything good is underneath calc. So I'm going to hit second calc. Now you look right there. Number 6 is dy dx. So I can hit dy dx, and then it'll ask you what x value you want to figure out. So I want to figure out what's happening at -2. So I just type in -2. And it spits back the same answer we found the long way. Or not the long way, but from the main screen, -38. So you can do this graphically, or you can do this algebraic, or from the main screen. Sometimes you need to have your graph on the calc, so it's easier just to type in from where that derivative is. Now, as usual, nothing's ever easy. Let's try the next one. So here I am. I'm going to try to do the derivative according to x of x to the 1/3 at 0. All right, we get 100, right? Life is good. Yay. Y prime of 0 equals 100. No, no good. Nope. Now, how are you supposed to know that? How do you know that that is actually, the calculator told us it? Why is the calculator wrong? It's because you've got to remember what the sketch of 1/3 looks like. So I'm going to, again, like we did here, I want to get an idea of if this answer seems reasonable. So let's sketch the graph of 1/3. Now this one might not be as easy to remember, but think about who it's related to. Pause it, give yourself 10 seconds, and then either draw it or give up. All right, well, hopefully you drew it. Here's how I think about 1/3. It's the inverse of to the third. So to the third looks like this. So the cube root of that, the inverse of that, is going to look like this. It's going to be going sideways instead of up and down. So what do we want to figure out the tangent line? Well, we want to figure out the tangent line as x approaches 0. The problem here is that the tangent line, so I've got my tangent. Maybe I could use this. There's my tangent line. 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 Uh-oh. What's happening to the slope of my tangent line as we get closer and closer to 0? Eventually we get vertical. We have a vertical tangent line here. Vertical tangent line at x equals 0, exclamation point. That's a big deal, because what does that mean our derivative is? What's the slope of a tangent line? It doesn't exist. So y prime of 0 would actually equal DNE. So if I was a student, my next question would be, well, how the heck was I supposed to know that? That's a fair question. That's why I usually do my derivatives from the graph, so that I can take a look at the graph and see if it seems reasonable. So I would have gone here, x to the 1/3. I would have graphed it so that I had an idea of what the picture looked like. And then when I looked at the derivative, it kind of makes sense. I mean, think about it. Does the slope of the tangent line there have a slope of 100? No. Oh, dang it. Sorry. I'm on the wrong. You guys didn't even see what I did. Sorry. So what I did was I graphed the graph of x to the 1/3. No, the slope of the tangent line there isn't 100, right? Rise 100, run. There is no, it's vertical. So that would be a warning sign to me. And you'll get better. You'll start to recognize these over time, the more we do of them. So which of the preceding values are correct and which ones are incorrect? We just kind of talked about that. Make sure that you have an idea of what the graph looks like so that you can figure out what the slope of the tangent lines are. I mean, if we made a sketch of this graph, I don't want to go back. Yeah, it'll take 2 seconds. Let's just sketch it. What's the, no, this is going to be tough to sketch. Never mind. I really don't want to do that because it'd have an SA, right? The HA would be infinity because there's more X's on the top. I do not want to sketch that, but hopefully you get the idea. Now, what's nice is you can use your calculator to sketch the derivative of a function. So what we're going to do is we're going to ask our calculator to sketch the derivative of this. So when we type it in, we're going to now name our equation the derivative. So I'm going to go alpha f2, sorry, and I'm going to put the derivative right in there. So my equation is going to be the derivative of the function that they gave us. So it's going to graph the derivative for us. So I'm going to select x, deriving according to x. My function is negative cosine. Be careful with cosine because it brings up a parenthesis that you have to close. Now think about this. What do we want x to be? Well, if I put a number in there, it's just going to give me a number, the derivative at a specific spot. I want to figure out the derivative for when x is every x number. So what I'm going to actually do is I'm going to leave that as an x. So when I want to graph the derivative, I want to type in the derivative formula just like we would do on the main page, but then I want to derive it as x approaches x, and now I get a graph. Now it takes so long because your calculator is thinking really hard. It's doing the derivative of all the cosine points, and so it does take a little while to graph it. But that's a pretty famous graph. Let's make a sketch first and then try to figure out what the equation, because we're supposed to use the calculator to sketch it, and then we're going to use the graph to identify the derivative. Well, let's make a little note to how we wrote this in there. We wrote that y1 was equal to dd, and then I'm going to put in a different color all the stuff you need to add. ddx of, and then our function is negative cosine of x when x equals x. I wish I would have written that x better. If I want to graph the derivative, this is how we graph the derivative. I do the derivative feature from my calculator, and I make sure that I have x approaching x in the equation. All right, so let's see. We had a function. I'm going to bring this back up now. Our curve looked kind of like this. Hopefully you're recognizing what family this is. It's got to be a what or a what graph. It's either a sine or a cosine graph for sure. Now the question is, which one is it? Well, what's happening at 0 should be a dead giveaway. On your unit circle, when we're over here at 0, this is the point 1 comma 0. Is the x or the y 0 there? The y is 0, which means this is the sine graph. So it turns out, what did we just figure out? We figured out that the derivative of cosine is sine. So f prime of x would equal sine of x. And we should probably check a few points just to make sure. Let's check a few points on the graph to make sure it makes sense with what we know about the unit circle. So let's trace to 0. Yep, the y value is 0. Let's trace to 90. Now we have to talk about radians here, so you need to be in radian mode. That's 1. Again, remember, this is really 1. And what is sine at 90? It's 1. Let's go to pi, back to 0. Let's go to 3 pi over 2, should be negative 1. That's negative 1. I know it doesn't look like it, but that's negative 1. And then let's go to 2 pi. Yep, that's how sine works around the unit circle. So this graph is the graph of sine. Let's have you try the next one. Practice writing it in the calculator first. All right, let's see how you did. Y equals d dx of 0.25 x to the fourth when x is equal to x. Alrighty. Now what we're trying to do here is we're trying to figure out what the graph looks like by only inputting the derivative. As x approaches x, here's my graph. Yep, this is a graph that we actually just talked about earlier in these notes. What graph is that? That's the x cubed graph. Let's double check. Let's test a couple points to make sure. Like, what's 1 cubed? 1, good. What's 2 cubed? 2 times 2 is 4, times 2 should be 8. Nice. What's 3 cubed? 3 times 3 is 9, times 3 is 27. Let's try negative 2, negative 8, negative 3, negative 27. I think that's probably enough evidence. So we can now say that f prime, y prime is equal to x cubed. Let's have you try the next one. All right, pause it if you haven't yet. Let's see how you did. So I like to use this fraction feature, x, and now I got to use my absolute value feature over 2 as x approaches x. Here's my sketch. Oh, I know what that is. I know what that is. So, what did you get? I would get that y prime equals the absolute value of x. Before I box it in, I'm going to test a couple points. I'm going to trace to 1, and I get 1 and 2, 2, 3, 3, negative 2, 2, negative 6, 6. Yeah, we're in good shape. Okay, so sometimes when we have a particularly ugly function, ding, 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 look at this bad boy, and we are interested in finding information about its derivative, we can use the calculator's number crunching ability to an even greater degree. Okay, so what I'm going to do is I'm going to store this as my function in my equation. I'm going to go to my grapher. I'm going to put this in there first. Alpha sine of x. I really wish he would have written that better. It's not clear at all where the... I got to double check so we don't make a mistake here. I'm going to pause for a sec. All right, I think I got it figured out. This is very poor. You ever see those Facebook posts where it's like they put up a bunch of numbers and it's like 10 divided by 2 plus 7, so, or more like 10 plus 7. It looks something like this, like 10 plus 7 times 3, and people have a great battle about what the actual answer is. Well, 10 plus 7 is 17 times 3. No, you got to follow the order of operations. Anyway, when you write something like this, you're not being very clear mathematically on what you're trying to say, and I think Corpy got into that mess here. The thing that's confusing about this is what is getting signed. I'm going to assume that this is what he means. This is what my math voice is saying. That whole thing should be getting signed. Whether that's actually true what he wanted to do or not, I don't know, but I'm going to change it to this. Okay, so now I'm going to use my calculator to help me figure out the second derivative of the function at x equals 1, which we call f double prime or f prime prime. F double prime. Nobody ever says f prime prime. All right, so what I'm going to do first, I'm going to tell my calculator that I want to draw the derivative of this function. So I would go derivative according to x of, and like I said, I like to put the fraction in there. I'm going to do sine of x times the square root of x squared plus 1. I don't know why I typed 2. Over e to the x. And because I want to figure the derivative everywhere, I only want to figure out the second derivative at 1. I want to figure out the derivative everywhere, so I'm going to leave this as x. Now, there's a couple of ways to go from here. If you want, you can go into this column, and you can then do the derivative of this. Another thing you could have done is put the derivative of the derivative in there. That's another way to do this. I'm going to then take this, and I'm going to store it out in my other equation. So what I mean, let me show you what I mean. I'm going to now go derivative according to x of, now because I left this equation as y1, I don't have to retype the whole thing. In here, if you see this button VARS, that stands for variables. When you select that, you can go over to your y variables, select your function, and hit y1, and all of a sudden it takes all that junk and it stores it in that space. I want to evaluate this now. I'm not trying to graph the second derivative. I'm trying to evaluate the second derivative at 1. So I can type this in, and I can figure out that f double prime of 1 equals negative 1.413. In AP Calculus, the College Board expects you to truncate, not round. So this 3 I know can get rounded up to a 4, but you shouldn't. You go to 3 decimal places and you just truncate, which means chop it off, and you only look at those first couple numbers. Nasty, right? Let me see. Let me show you another trick here. Let's see. So I could also, if I want to take the second derivative, I could take the derivative. Oops, not the absolute value. The derivative, according to x, of the derivative according to x of my function. Why did I pick such a messy function to show this? Sine of x, or I could have just used y1 again. No, I couldn't because that's already the derivative. X times the square root of x squared. Ooh, I don't know if it'll let me do that. I'm going to do x times x. Something looks weird there. I didn't like that. X times x plus 1 over e to the x. Okay, now here's where it gets a little tricky. You got to pay attention to details. This first derivative, I'm not trying to derive it anywhere specific. So I'm going to derive this one according to x. Then this derivative, that's the second derivative. I want to derive that one specifically at 1, and it spits back exactly the same answer. So I did the derivative of the derivative, and the inside derivative, let me go back to the beginning. I did the derivative of the derivative of my function, but the inside function, the one I'm doing the first derivative, I derived everywhere, which is when x is x. And then the second one is I got more specific at when x is 1, and that's how we got the same value. So there's a couple different ways. Anyway, the idea here is just to have this idea that I can use my calculator to do some of the heavy lifting when it comes to evaluating the derivative at a specific spot. Most of the time, you're not going to be able to use your calculator, but sometimes you actually are. All right, so there you go. Quick notes. Hopefully the homework assignment is just as quick. Good luck.